life is truly a miracle. I mean, God's greatest miracle was the creation of life. Created this entire cosmos just to create life here on this planet, to create us, to have a relationship with us. It's truly a miracle. But the origin of that life, as far as evolution is concerned, is a linchpin. A linchpin under which the entire theory of evolution collapses for lack of foundation. Because at this point, they can't give us any reasonable explanations as to how life originated. In fact, they are at such a loss to explain it that they try to avoid the subject altogether. If you bring up the origin of life to evolutionists, they will try to claim that the origin of life has nothing to do with evolution. They will try to make that claim. But the origin of life is a necessary part of, when you talk about life, even the evolution of that life, the origin of life is clearly part of evolution. When I took evolution in graduate school, I took evolutionary biology in graduate school, the book we used had 2 chapters on the origin of life. And I challenge you to find any biology book used today in schools that does not address the origin of life in their unit on evolution. It's clearly part of it. But as a debate strategy, they will try to claim that it's not part of evolution, but it clearly is. So don't let them pull that stuff on you. But we're going to talk about evolution and particularly focusing on the origin of life and how the evolutionists attempt to explain this. Okay, so first we need to kind of lay some groundwork. The evolutionists generally claim that the Earth has been here about 4.6 billion years, and that life started as far back as 4 billion years ago. 3.7, 3.9, but or somewhere close to 4 billion years ago, life is believed to have originated on planet Earth. And it can be described as really in chemistry terms. So we're going to be talking a lot of chemistry. And, you know, John's over here doing all the fun stuff with fossils, and I get stuck with all the chemistry. But you're going to get a little science here today. I hope you expected that. But in general, evolution can be described in chemical terms. An increase in the complexity of the genetics that organisms have. It can be described generally in chemistry terms. And certainly its beginning must be described in chemistry terms. And that's what they try to do. It's what's known as chemical evolution in the beginning. But the origin of life is thought to have occurred through 2 primary mechanisms, and some claim a third as well. Chance is thought to have played an overwhelming part in the origin of life, but also what is defined as necessity. So chance and necessity, or the scientific laws that govern how molecules react with one another, how atoms combine and how subsequent molecules would interact with one another, that these basic laws of chemistry would have determined how these early molecules would have formed and how the first cell ultimately would have formed. Some try to invoke natural selection, although natural selection can't play a part until you have a reproducing cell, a cell that can copy itself, or at least a molecule that can reproduce itself. Natural selection couldn't be a part. And of course they need lots and lots of time. Lots and lots of time for these processes to take place. So let's walk through the general scenario real briefly. They ultimately begin their scenario with molecular evolution, with what's known as chemical evolution. Initially, molecules would have formed in some kind of thick primordial soup. A soup that a concentration of molecules would have developed somewhere, and things like amino acids and nucleotides would have formed in that soup. These are the building blocks for proteins and DNA, these molecules are. And then subsequently, these molecules, these amino acids and nucleotides, would have joined together to form chains. That's what most of the big macromolecules are chains of smaller molecules. Protein is a long chain, DNA is a long chain, fat molecules, lipids are long chains, and so what we call polymers. Then these big macromolecules would have aggregated together and formed ultimately the first cell, a cell like a bacteria. A bacteria is believed to be probably the first cell, perhaps a photosynthetic bacteria. All life on Earth is believed to have evolved or developed from one single ancestral cell, known as the last universal ancestor, probably a photosynthetic bacteria. That's generally what's suspected. And then one of these these bacterial cells would have formed symbiotic relationships with one another, forming the first eukaryotic cell, which are the kinds of cells that we have. Our cells have little organelles inside them, like mitochondria, and plants have chloroplast. It is believed that these organelles were once bacteria. That one bacteria ate another bacteria, and then it started living inside of it, and they developed a symbiotic relationship, and it's generally referred to as endosymbiosis. Okay? So, but then after this eukaryotic cell formed through this process called endosymbiosis, colonies of eukaryotics would have gathered together and fused and ultimately formed a multicellular organism, where each one of those cells would have eventually developed specialized functions. That's the general scenario. And before I start talking about problems, let me show you what they can support. There are examples of endosymbiosis, examples where one cell actually internalizes another. This euglena, this single-cell organism, does not make chlorophyll, is not itself naturally green. But it eats algae. You can actually see it gulp one in here at some point. It eats algae, and then instead of digesting them, it keeps them inside, and the algae performs photosynthesis, and then the eukaryote here can actually benefit from the products of photosynthesis that the algae are performing. And it's not the only one. There's a plant also that forms a symbiotic relationship with bacteria. The nitrogen fixers, legumes such as soybean, bacteria actually invade plant cells, and then the cell changes to harbor the bacteria. The bacteria can absorb nitrogen from the atmosphere, and then the plant can take advantage of that. And it's a complex relationship. There are also examples where single-cell organisms form what, for all intents and purposes, are multicellular types of structures. This is a lengthy video, and I always debate whether to show it, but these are single-cell organisms, the amoeboid type cells. Instead of having the swimming around with cilia like that one just a second ago, these ooze off in whatever direction they want to go in. Your white blood cells are very similar. They're amoeboid like those cells you just saw. But what these do is they all gather together and form a multicellular type of structure called a slug. And you'll see it here in a second. There's a whole bunch of them fusing together, making the little slugs. Notice the slime mold. They're in this area. If you know what to look for, you can find slime mold, little slimy thing, like usually yellow, and you'll see them in the rainforest, in the dense wet forest around here. You can find slime molds. But to form the slug here, and then I'll give you a chance to see this. This is actually pretty cool. So I think you'll say, "Oh, that's very." So I wouldn't have dropped the time on a video. And this is sped up. This is sped up a little bit. They're not actually moving this fast. So you see, these two aren't running to catch up with the other ones. Wait, where are you going? Don't leave me. I'm stuck. Wait. That's sped up. That's sped up. So there's your slug. You can still see some others trying to merge with the slug, but it forms what, for all intents and purposes, is a multicellular type structure. But that's not the end of it. When this slug finds a suitable location, it forms what's like a plant. It actually forms a plant-like structure, a stalk with a basically reproducing structure at the top, a spore-producing structure that then, in which spores are produced, and it'll pop, rupture, and send spores flying out. There's two of them that merge together. They're not. All right, show us the next one. So it'll show you a bunch of them that. Now these are all mature now. They've all developed a substantial mass, and they found a suitable location. And now you'll see a couple of them here starts to stretch up. They'll all stretch up into the air, and they'll form a head, a reproductive structure that contains spores. And that's pretty cool, right? I mean, biology is really cool. We learned a lot. As science progresses, we learn more and more about God's creation and what a wonderful thing it is that He made. He made organisms with some amazing abilities. I don't believe this is evidence that that multicellular organisms have evolved from single-cell organisms, but nonetheless, it is still pretty cool stuff. And I wanted to show you what they can support. There is endosymbiosis is a powerful argument. My major professor, when I was in graduate school at Texas Tech, he he found out I was a creationist, and he made me take evolutionary biology, which I was glad that he did, because but after I had taken the course, he asked me later. He said, "So now are you convinced that evolution is true?" And I said, "No." And he said, "Well, what about endosymbiosis? Hasn't that proven evolution, where one cell internalizes another?" And I couldn't really respond to his question, but we're skipping some big steps. You know, endosymbiosis is way down the road a little bit. You know, what about that first cell? What about all those big macromolecules like proteins and DNA? You know, we're skipping a bunch of steps here, and I wished I had been able to give him a proper answer. But what about that first cell? Cells must do a lot of things to be a cell. They must be able to reproduce, number one, which means you got to be able to copy everything you have. That requires a lot of machinery. And that machinery requires a lot of energy. You got to be able to make a lot of energy to power all those machines. You have to be able to make the machines. And to make those machines, you need information to tell you how to make those machines. Cells got to be able to do a lot of stuff. But is there any evidentiary support for the origin of that first cell? Or is it just a lot of assumption? Franklin Harold is a professor of biochemistry and molecular biology at Colorado State University. He says, "Life arose here on Earth from inanimate matter by some kind of evolutionary process about 4 billion years ago. This is not a statement of demonstrable fact, but an assumption almost universally shared by specialists as well as scientists in general. It is not supported by any direct evidence, nor is it likely to be, but it is consistent with what evidence we do have. An assumption almost universally shared, but totally lacking in evidence." Isn't that telling? Now, a lot of theories have been put forth about how the first cell formed. Early theories were very optimistic because back in Darwin's day, they really didn't know what we know about the cell. Ernest Haeckel was arguably the most famous evolutionist of Darwin's day, and he describes the cell like this, that it was not composed of any organs at all. Describing bacteria. Ernest Haeckel named the kingdom Monera, the bacterial kingdom, the kingdom Monera, and he describes bacteria like this. But they consist entirely of shapeless, simple, homogeneous matter. They're nothing more than a shapeless, mobile little lump of mucus or slime, consisting of albuminous combinations of carbon. When you think of the cell as nothing but a little lump of mucus or slime, it's pretty easy to try to explain the formation of such a thing. But now we know that the cell is tremendously more complex than anyone in Darwin's day knew. They didn't even know of DNA at that point in time. They didn't know even of these big macromolecules. Countless more moving parts than any of the marvels of modern technology. Evolutionists realize this now. Michael Denton, in his book, Evolution, a Theory in Crisis, describes the cell in these terms. To grasp the reality of life as has been revealed by molecular biology, we must magnify a cell 1,000 million times until it is 20 kilometers in diameter and resembles a giant airship large enough to cover a great city like London or New York. What we would then see would be an object of unparalleled complexity and adaptive design. Unparalleled complexity. That's what the cell is like. We have seen nothing like it. It's unparalleled in its complexity. Evolutionists realize this, but still, they've been optimistic about how life originated. One of the first major thinkers that worked on the origin of life was Alexander Oparin. His major contribution was a theory known as the coacervate theory of the origin of the first cell. He proposed that oil molecules, lipid molecules more specifically, they would spontaneously form little droplets. And in doing so, they could trap the things that were in the solution, potentially proteins if those existed. Those oil molecules forming a nice little membrane around some proteins and possibly could have explained the origin of the first cell. Oparin, back as early as the 1920s, established what today are still the major tenets of the origin of life theories. And I'll try to give you this in brief. Excuse me. There is no fundamental difference between a living organism and lifeless matter. The complex combinations so characteristic of life must have originated in the process of chemical evolution. When you start with the a philosophical worldview such as it must have arisen by a specific process, that limits your theories to specific types. And of course, that's what scientists are today, are naturalists, and they must explain our world through philosophical naturalism. The infant Earth possessed a strongly reducing atmosphere. I'll describe what that means and why he said that here in a little bit. Initially, there were simple organic solutions governed by their properties, the arrangements of their atoms. But gradually, as a result of growth and increased complexity, the molecules developed new properties which determined their spatial arrangement and the mutual relationship of the molecules. That the properties of the atoms and molecules ultimately determined how they came together. Chance and the scientific laws of chemistry governed or determined how life originated. And lastly, that competition, speed of growth, survival of the fittest, struggle for existence, and the natural selection determine the material organization which is characteristic of living things. Natural selection. Chance, chemical processes, the properties of chemicals, and natural selection. But like I said, natural selection couldn't play a part until you have a cell, until a reproducing cell. But nonetheless, that's how they view things. And all origin of life theories basically still holds to these principles. One of the first major experiments to be put forth to try to explain how some of the early molecules of life performed was performed by Stanley Miller, a graduate student, and his professor Harold Urey in the 1950s. They won the Nobel Prize, if memory serves, I think in 1956 for this particular experiment. They put together an apparatus which they hope would explain how building blocks of life would have formed in an atmosphere similar to the one they believed the Earth had in its infancy. And so what they did was they constructed this apparatus and they stuck several chemicals inside, methane as a carbon source, ammonia as a nitrogen source. They added hydrogen gas, and then they added some water vapor by way of a boiling flask down here. And then they added some energy by way of a spark chamber, a condenser to condense the vapor back into liquid, and then a collection chamber where they could remove unwanted substances and then eventually the products. And they formed some amino acids. When they finally collected it, some amino acids had formed, which are the building blocks for proteins. And biology textbooks still hail this as a major achievement of evolutionary biology, or of the origin of life theories, although has been largely discredited today. Prentice Hall Biology, 2008 edition. Prentice Hall Biology is arguably the most widely used biology textbook used in public schools today. I think that's an accurate statement. Over a few days, several amino acids, the building blocks of proteins, began to accumulate. Miller and Urey's experiment suggested how mixtures of organic compounds necessary for life could have arisen from simpler compounds present on the primitive Earth. There are a number of problems, however, with this experiment, although it did produce some amino acids. Probably not the least of which is the fact that in any kind of chemical reaction like this, you're going to get two types of amino acids, what are typically called dextrorotatory and levorotatory molecules. They form races, or it's called racemization. They form what are left and right-handed type molecules. Mirror images of one another form. But in all life forms on Earth, only the left-handed amino acid is formed. Only left-handed amino acids. And they've tried to get amino acids to form under all kinds of conditions where only left-handed amino acids would form, and they can only shift the percentage slightly, like 60% left-handed amino acids and 40%. But life forms don't have just more left-handed amino acids, they have all left-handed amino acids. And if you start off with a pool of left-handed amino acids, they spontaneously revert or change to right-handed amino acids until they reach equilibrium, a 50-50% solution. And so it's a major problem. But if you remember his little apparatus, they were simulating an early atmosphere that contained methane, ammonia, hydrogen gas, and water vapor, but there was one thing obviously missing from that's in the atmosphere. What is that? They eliminated oxygen intently because they know that amino acids won't form in the presence of oxygen. Oxygen is an oxidizer. An oxidizer is a substance that will strip electrons from other molecules. And in doing so, it will promote chemical reactions or destroy molecules. And amino acids won't form in the presence of oxygen. If oxygen is present, the amino acids that are there are going to be destroyed. Okay, they know this, and that's why Oparin said that the Earth probably had a reducing atmosphere. Just basic chemistry, we know that amino acids, the building blocks of molecular life, would not form in the presence of oxygen. The problem with this, initially they assumed that the Earth must have had a reducing atmosphere, but now it's relatively clear that it never did. The journal, the Bulletin of American Meteorological Society in '82, geologists know from their analysis of the oldest known rocks that oxygen levels of the early atmosphere had to be much higher than previously calculated. From the journal Geology, there is no scientific proof that Earth ever had a non-oxygen atmosphere such as evolutionists require. This is a secular journal, Geology. Earth's oldest rocks contain evidence of being formed in an oxygen atmosphere. They have minerals that are just known as oxides. They check deeper and deeper. All the rocks that they find always seem to have oxygen. It would appear that oxygen has always been present. This creates a problem, though, because if amino acids won't form in the presence of oxygen, but life can't exist without oxygen for other reasons. We need oxygen to, of course we breathe oxygen, but there are bacteria that can live without oxygen, called anaerobes. But oxygen is required for another reason, to protect us from that big thing up there. What is the oxygen that protects us from that big thing? What's it called? The ozone. Yeah, we need the ozone layer to protect us from UV bombardment, which will destroy any life form or any of these big macromolecules, just be nuked by UV radiation. We need that ozone up there. So, but they're relatively, at this point, they know that Earth seems to always had oxygen. That itself is a big mystery. So where then did it form? Of course, theories have shifted. Dyson is a professor at the Institute of Advanced Studies at Princeton University and a member of the National Academies of Science. He said, since Miller's beguiling picture of a pond of dissolved amino acids under a reducing atmosphere has been discredited, although Prentice Hall Biology didn't appear to think so, a new beguiling picture has come to take its place. The new picture has life originating in a hot, deep, dark little hole on the ocean floor, which is where, their hopes have lied for some significant period of time, such as these black smokers, geothermal vents that they discovered in the 80s on the bottom of the ocean floor. Tremendous energy being generated there, and whole communities of organisms will sprout up around these things. So there was a hope there. The problem with this theory, though, is that the reaction that joins amino acids together to make a chain of amino acids is called a condensation reaction. When you join amino acids together, water comes off. They're condensed, and water is given off. The opposite of this, if you add water to a chain of amino acids, it cuts them apart. It's called hydrolysis. Water cutting. Hydrolysis will basically cut apart two amino acids. So amino acids won't form in the presence of oxygen. Chains of amino acids won't form in water. So we're kind of stuck. And it goes even further. Remember that life forms need big macromolecules, not just these little building blocks. They need chains, these big polymers. And Miller's experiment produced no polypeptides or peptides or chains of amino acids. None of these were produced in the Miller experiment, but that's what are required. Proteins, though, are not just chains of amino acids. It's a much more complex structure than that. A chain of amino acids is ultimately folded into several types of functional shapes, like that beta-pleated sheet or the alpha helices. And several of these are used to make what is known as a tertiary structure, which is itself a subunit of a larger protein. Many genes are required to make a protein. The protein itself is a very, very complex molecule. Making it is a very, very sophisticated process involving a great many other proteins. Proteins are necessary to make other proteins. But we can look at this probabilistically. Assuming, though, that there is an environment where a chain of amino acids will form, what is the probability of getting a functional chain of amino acids, a specific protein that we want? What are the probabilities? We can look at this, and from a probabilistic, this is how probabilities work. I flesh it out for you a little bit using an analogy. To calculate the probability of an event, you can use this formula right here, where the number represents how many possible outcomes there could be. In the case of flipping a coin, there's head and tails, so you have two possible outcomes. and then you raise that number to the power of how many specific outcomes you want. Meaning, if I want 2 heads in a row, then it's 2 to the second power, or 1 chance out of 4. Okay? To get 3 heads in a row, of course, that's 2 to the third power, which is 8. If I want to get 8 heads in a row, that's 2 to the 8th power, which is 2 times 2 times 2 times 2 times 2, right, is 256. If I want to get 100 heads in the row, again, that's 2 to the 100th power, or what is 1 chance out of 10 to the 30th power, which is 10 multiplied by itself 30 times, or a 10 basically with 30 zeros after, right? That's a huge number. You would have to flip a penny 30 million times a second for over 1 quadrillion years to reach the probability of being able to get 100 heads in a row, just to give you an idea how big that molecule is. So what about a chain of amino acids? Okay, this is there probably are chains of amino acids that are only 150 units long, but most proteins are much, much larger than this. So we're really getting conservative here. But what are the probabilities of getting a chain of amino acids 150 long? To calculate this, we need to take several things into consideration. It's a little more complex, but these numbers are impressive, and it's a good thing to review them. So there are 2 kinds of bonds that can form between amino acids. So there's peptide bond and then other types of bonds that can form. And as it turns out, there's about 50% chance of forming a peptide bond between 2 amino acids as opposed to some other kind of bond. So chance of 2, 1 out of 2 types of bonds, 150 amino acids, we get a probability of 1 out of 10 to the 45th power. Okay? Remember, we can only have L amino acids, not L, and there's L and D could form. So that's, again, there's 2 different outcomes there. At raised to the 150th power, we again have the probability 1 out of 10 to the 45th of just getting a chain of amino acids 150 long with only L amino acids. Are you following? Sorry about this. We gotta do this. So to get the correct amino acid sequence, there are 20 amino acids. What is the probability of getting the correct 20 amino acids in a chain that's 150 long? That would be 20 to the 150th power, or 1 out of 10 to the 195th. But to be completely fair and accurate with our calculations, we now know that some amino acids can be substituted for some others, and the protein still remain its function. By doing what are called mutagenesis studies, they can mutate genes intentionally and see how many mutations the organism can survive with, or in this case, how many the protein can tolerate and still be functional. By doing this, they were able to adjust this value and determine the tolerance limit of a protein to substitute amino acids. So we've adjusted this number, and we're going to substitute it with this one, a much more conservative number. Okay, so to get a chain of amino acids, 150 units long, we would basically multiply that number by that number and then this number together, or basically you just add up the exponents to come up with your number, and you get the whopping number of 1 out of 10 to the 164th power. It's just an absolutely enormous number. And the law of probability states that any odds greater than 1 out of 10 to the 50th power is not possible. That's what the law of probability currently calculates. So evolutionists realize this. Francis Crick was one of the co-discoverers of the DNA helix. James Watson and Francis Crick discovered what the DNA molecule looked like. There was a race. Lots of people were working on it. They beat out everyone else. But he says that if a particular amino acid sequence was selected by chance, how rare an event would this be? The great majority of sequences can never have been synthesized at all at any times. But it's a big universe, and according to evolutionists, a very old universe. They believe that it's 13.7 billion years old. That's current calculations, and there's a lot of galaxies, lots of matter out there. To be honest with this, we got to take into consideration what are known as the probabilistic resources. The probability of getting 100 heads in a row is really, really small. But what if you got a billion people working on it? Does that bring it down to a probability that becomes a possibility? Okay, to know whether or not it's really possible to get a chain of amino acids 150 units long, we got to take into consideration what are known as probabilistic resources of the universe. And these are fairly easy to calculate. You only need 3 things. How many particles are there in the universe? There's 10 to the 80th particles in the known universe, atoms in the known universe. How much time has there been since the beginning of the universe? If the universe is 13.7 billion years old, I don't believe that is either. But there's 10 to the 16th seconds in 13.7 billion years. And this number is a little technical, and I won't bore you with it. It's all based on what's called Planck time. But the number of events that could take place per second is 10 to the 43rd. So that's a really big number, but that's based on physics, the maximum number of events that could take place per second. Okay? So to determine the probabilistic resources of the universe, you basically multiply those three together, and that's the probabilistic resource of the universe. But our number is still overwhelmingly larger than that. And so there has just not been enough time. There is not enough matter in the universe, nor have there been enough opportunities for chemical reactions for even one chain of amino acids to form. They're just not there. Now, my main resource for this presentation was Stephen Meyer's book, Signature in the Cell, which was published about a year ago. Stephen Meyer's an absolute brilliant man. And the book itself is on the origin of life. And I think it's going to become a very, very important work, probably a seminal book for all future work on not only the design of the cell itself, the arguments for intelligent design from the cell, but in particular the problems that still lie with regard to the origin of the universe. A few comments from Stephen Meyer.
In the 19th century, biologists thought that cells were simple, homogeneous globules of plasm. Now, with that kind of understanding of life, it was easy to imagine how life might have arisen through a few simple chemical reactions, and the origin of life was no big problem. Post-1953, with the discovery of the structure of DNA and also the information-bearing properties of DNA, we can no longer look at the cell the same way. And what we're now discovering is that the cell is chock full of exquisite miniature machines, little turbines, little rotary engines, little walking robots that cart materials from one end of the cell to another. Now, in our experience, all of those kinds of entities are produced by one cause and only one cause, and that is intelligence. And that, again, challenges materialism, because the materialistic worldview of the 19th century said there's two fundamental realities, matter and energy. What we're now discovering is that there's a third fundamental reality, and that is information. And everything we know about information is that it must come from an intelligent cause. So the presence of information in living systems suggests an intelligence that preexists us, that is responsible for all that exquisite nanotechnology and information.
The existence of information in the cell is arguably one of the best evidences of intelligent design, but also all of those little molecular machines as well. So the information in the cell is what kind of molecule serves as the information for the cell? DNA. And where does DNA exist inside of a cell? Right there in the nucleus. DNA, of course, is this double helix structure, the one that was eventually determined by Francis Crick, as I mentioned previously. And just to give you an idea how much information there is in DNA, in a single human cell, there's about as much information as there is in 1,000 books in one human cell. The chromosomes in a human cell range in size from 1.7 to 8.5 centimeters in length. In one human cell, if you put the DNA molecules together one after the other, you will get a string that's about 6 feet long in one human cell. But in that one string, little miniature microscopic string, there's about as much information as in 1,000 books. You can look at this another way. A 2-millimeter pile of DNA, which is about as big as a pinhead, has about as much information as there are in 500 stacks of books reaching the moon, or a single stack of books reaching the sun. It's an incredible amount of information. And it is truly information. We can draw a lot of parallels between the information that's in DNA and our own language structure as well. The DNA is basically arranged in what are similar to sentences. Those sentences, basically, we call them genes. There are about 1,000 genes on a single human chromosome, little less on some. But the gene is basically an instruction that tells a cell how to make proteins. That's what it is. It's an instruction that cellular machinery will use to make proteins, which are themselves the cellular machinery. All right? So Basically, the sentence or the gene works like this. Within that sentence, there are little words known as codons. At the beginning of the gene, there's always a code that tells the cell where the gene begins, much like our sentences have a capital letter at the beginning to tell us where they begin. And there's always a code at the end that tells the gene tells the cell where the gene ends. And there's also sequences upstream of the gene that tell the cell when to make a protein, how much protein to make, and what to do with that protein when it's done with it. What the intended use of that protein is, where the cell is supposed to take it. All of that information is there along with just the basic sentence. But the sentence provides, again, information on how to make proteins, which are themselves a chain of amino acids. Okay? So it works like this. If the cell reads the gene and finds the code UGC, it will insert cysteine into the protein that it's making. And if it finds the code CUG, it will insert the amino acid leucine. And if it finds AGU, serine. And if it finds CGA, alanine. So it reads this sentence and uses that to make a protein. And proteins are the machinery and the material that make life possible. All of the work that's done in the cell is done by proteins. And they are also the building blocks for a lot of important things as well. Your hair, your fingernails are all basically made of pure protein. Okay? But so they're the building blocks as well. They're the machinery that makes life possible. Stephen Meyer introduces the concept DNA enigma in his book, and I'm going to try to give you the basis for that a little bit, although he explains it a lot better. But his basic argument for design from information kind of reads like this. Experience shows us that large amounts of specified complexity or information invariably originate from an intelligent source, from a mind or a personal agent. Since intelligence is the only known cause of specified information, at least from a non-biological source, the presence of specified information-rich sequences and even the simplest living systems points definitively to the past existence and activity of a designing intelligence. Because all the information we know of comes from an intelligent source, it's reasonable to infer that because we have found information in a cell, that information also originated from an intelligent source. That's a reasonable inference. And it's a powerful argument for intelligent design. But it's not just the DNA, the information that must be explained, but an entire information processing system within the cell. There's a system there to read that information and then do stuff with it. And even software programmers today, like Bill Gates, recognize the sophistication of this system. He says DNA is like a computer program, but far, far more sophisticated than any software ever created. So this is a little animation from Unlocking the Mystery of Life that walks through the basic process that this information processing system goes through to use the DNA. And there's some important things in here. And so this is the nucleus, where the DNA is contained within a cell, and now it's going to enter the nucleus, and we'll see the DNA in there. Again, the DNA is basically two strands of molecules that are running parallel to one another, and then the thing is twisted into a helix. So that's the DNA molecule, but there are two strands. In order for the cell to get in there and read one of the strands, first it has to be unwound. The helix has to be uncoiled. And that's done by a large molecule called DNA helicase. So helicase comes in, uncoils the DNA, and then a large complex form, the main enzyme being one called RNA polymerase, which will then read the gene and make a copy of it. It wants to use that information, but it doesn't want to remove it from the nucleus. So it makes a copy of it and sends that copy out to the machinery that are going to make the protein. It's called the messenger RNA. It's a message, a copy of the gene that's being sent outside the nucleus, so that then the machinery out there that will make a protein from it can read it. And then for some, it'll make several proteins out of it. There's a regulatory sequence that tells the cell how many proteins to make from this message, and then it'll be rapidly destroyed. Once it gets out of the nucleus, a machine known as a ribosome will assemble on the messenger RNA and begin reading the information. Another important molecule you'll see here is called a transfer RNA. It's actually bringing amino acids, which are the molecules on the end right there, to the ribosome, this machine that's making the protein. It also has a code, a matching code to that of the gene. If the code on this transfer RNA matches the code on the gene, if the amino acid is left and becomes part in the ribosome, catalyzes the attachment of that amino acid to the previous one, and it starts making a chain of amino acids. But a protein, remember, is not functional as just a chain of amino acids. It has to then process this chain. It has to fold it into various types of shapes, combine it with other subunits, and the machine that actually folds up the protein is called a chaperone or chaperonin. And this process is not well understood at all. But there are enzymes inside the cell that catalyze the folding of this protein, and then once it gets done with that, another will come along and transport the protein to the place within the cell where it's going to be needed. And then at the end of this, there are some comments from Dean Kenyon. So another molecule will come up and bond to this and then transport it to another part of the cell.
This is absolutely mind-boggling to perceive at this scale of size such a finely tuned apparatus, a device that bears the marks of intelligent design and manufacture. And we have the details of an immensely complex molecular realm of genetic information processing. And it's exactly this new realm of molecular genetics where we see the most compelling evidence of design on the Earth.
Dean Kenyon commenting in this video, again, this is a video from Unlocking the Mystery of Life, him commenting, and this is very significant. Dean Kenyon is one of the first people to write a major work, a book on the origin of life from natural processes. His assertion, known as biochemical predestination, was that these molecules that are present in biochemical systems were predestined to become the big macromolecules that cells need, and ultimately that life was predestined based on the scientific laws of their properties. And he ultimately became convinced, because of the sophistication of the cell, the evidence of design, the information that's within the cell, that ultimately it pointed to intelligent design. And now he's an advocate for intelligent design, although writing one of the first major works, Biochemical Predestination. Nonetheless, DNA Enigma, there's several other aspects to the DNA Enigma other than the fact that it's information, and that not only the cell has to be able to, we have to explain the origin of information and the information processing system, but in order to make protein, you have to have DNA, okay? But in order to make protein, you also have to have protein. In order to make DNA, you have to have DNA. In order to make protein, you have to have protein. In order to have protein, you have to have DNA. There's a vicious circle here where you have to have one. And it goes deeper than this. These chicken or the egg arguments apply almost throughout molecular biology. In order to have information, make information, you have to have, you have to have information. In order to make energy, you have to have energy. One of the important molecules in the cell, ATP, you have to have ATP to make ATP. You have to have DNA to make DNA. You have to have proteins to make proteins. Okay? Even RNA polymerase. Remember the enzyme that was making the messenger RNA? RNA polymerase, that protein right there. Remember we calculated the probability of a chain of amino acids 150 units long, 1 out of 10 to the 164th power. RNA polymerase is 3,000 amino acids long. 3,000. To build RNA polymerase, Stephen Meyer, for example, the cell must first transcribe the genetic text with the instructions for building RNA polymerase. Yet to transcribe the information requires the RNA polymerase. The information necessary to manufacture RNA and all the associated enzymes and protein cofactors of transcriptions is stored in the DNA template, but expressing that information on the DNA template for building the proteins of the transcription system requires most of the proteins of the transcription system. It's a huge problem. And evolutionists realize this. Even Karl Popper makes similar statements. Karl Popper is best known for his contributions to the scientific method known as Popperian falsification. That to validate one's theories, that you must be able to falsify them. Karl Popper says, what makes the origin of life and the genetic code a disturbing riddle is this. The genetic code is without any biological function unless it is translated. That is, unless it leads to the synthesis of proteins, whose structure is laid down by the code. But the machinery by which the cell translates the code consists of at least 50 macromolecular components which are themselves coded in the DNA. Thus, the code cannot be translated except by using certain products of its translation. This constitutes a baffling circle, a really vicious circle, it seems, for any attempt to form a model or theory of the genesis of the genetic code. Thus, he says, we might be faced with the possibility that the origin of life, like the origin of physics, becomes an impenetrable barrier to science and a residue to all attempts to reduce biology to chemistry and physics, which is what they try to do. Law-like processes and chance are alone responsible for these macromolecules and for life. To explain DNA, they must appeal to the properties of its molecules. DNA must have come into existence because the molecules that make up the DNA tended to form certain kinds of bonds with one another, ultimately leading to the DNA. But if you examine the structure of DNA, there's a problem here, part of the DNA enigma. This is what DNA looks like. It's two strands of molecules that basically run parallel to one another. And it's made up of 4 different types of subunits called nucleotides. And so there's one nucleotide there, another nucleotide there, another one there, another one there. These nucleotides are all the same, and they all contain the same sugar molecule called ribose. So they all contain a ribose, and they are unique from one another, and they all have a different base. Okay, there are 4 different nucleotides, different in that they all have a different base. These pair up next to one another across a bond here. But the backbone of the molecule is held together by a bond called a phosphate bond that links these sugar molecules together. So the molecule is held together by a bond that's identical amongst all the nucleotides. Yet the unique part of the DNA molecule, this base, between those, there are no bonds. There's nothing unique about the attachment of one nucleotide to the other. There are no chemical properties in the DNA that one can point to that suggest why one nucleotide is bonded to any other. They are bonded together at an identical bond, the backbone of the molecule. It's a problem. They can't explain the origin of DNA through just the properties of the molecules that make it up. To explain the information processing system, remember there's a relationship between DNA and proteins. The DNA has a code that is then translated into a chain of amino acids, right? To explain this system, at some point there needed to have been a direct relationship between that sequence on the DNA molecule and the sequence on the protein, meaning that the amino acid should have at some point in time been linking up with the DNA chain for this system to have eventually formed. If the protein formed first, maybe then nucleotides started bonding to it, and eventually the cell started using that as an information representation of the protein. Are you understanding me? Okay? The problem with that is amino acids don't link to nucleotides in this way. In the information processing system, the amino acid never comes into contact with the genetic code, ever. The molecule that brings the amino acid to the ribosome is this molecule transfer RNA. Remember in the video they were coming over and I told you what they were. This is a model of the transfer RNA. It has a little code that must match the genetic code at one end, but the amino acid is linked on the opposite end of the molecule. It never comes into contact with the genetic code, ever. Not only that, but the nucleotides that the amino acid bonds to are identical in every transfer RNA molecule. There are 20 amino acids used to make proteins. There are 20 unique transfer RNA molecules. They have a different code here, and they have a different amino acid up there. And in all 20 transfer RNA molecules, the same linkage is found here, an ACC. The nucleotides ACC are found up here. And also, the protein that makes transfer RNAs, there's 20 unique proteins that make transfer RNAs, called amino acyl synthetase. There are 20 unique. The system is very, very unique, very specific. There's a protein does only one job, and one job only, to make one thing. It's a very, very complex system involving countless numbers of proteins, and it's this that the evolutionists have to explain, the existence of all these proteins. So we looked at the probability of forming a single amino acid. Let's consider just for a moment the probability of forming that one enigmatic first cell. The simplest cell that we know of is a parasitic bacteria called Mycoplasma genitalium. It's a bacteria that parasitizes the human urinary tract. And it's the simplest cell that we know of. An obligate parasite, which means it can't live outside the human body. But it's very simple because of that. It doesn't need to make all of its own stuff. It's going to use a lot of yours, right? But it has 482 genes. That's still a lot of information. But through mutagenesis studies, by knocking out genes, they were able to figure out that it could live with 256. So it can live with the minimum of 256 genes. Okay, that's still a lot of information. That's still a lot of nucleotides. But remember what the probability was of getting one simple chain of amino acid to form through random processes, through chance and the interaction of molecules. What was it? You guys are listening. It warms the cockles of my heart. I tell you what. Remember, it's an obligate parasite. But assuming that these genes are really simple, all these proteins are really simple, little 150 amino acid long proteins. What the probability of this first cell then, assuming it needs a minimum of 250, which 256 was a limited number that times the 10 to the 164th power gives us a whopping number of 1 chance out of 10 to the 41,000 power. And these numbers are pretty much widely accepted. Robert Gange is professor of cryogenics and information systems. He says the likelihood of life having occurred through a chemical accident is for all intents and purposes 0. Remember, the law of probability says that anything smaller than 1 out of 10 to the 50th cannot happen. We're just so far above that, it's inconceivable. Joe McFadden is a professor of molecular biology and quantum physics. He says the simplest living cell could not have arisen by chance. If we did have all the DNA information that a cell needs, if we had all the protein that a cell needs, if you even have all the organelles, like mitochondria and things that a cell needs, you're still not going to be able to have a cell. You can't put all those together in a beaker and add a little bit of energy and get the first cell. There's more to life than just having a bunch of macromolecules. Klaus Dose is regarded as one of the foremost experts on the origin of life. He says, more than 30 years of experimentation on the origin of life in the fields of chemical and molecular evolution have led to a better perception of the immensity of the problem of the origin of life on Earth rather than its solution. At present, he says, all discussions on principal theories and experiments in the field either end in stalemate or in a confession of ignorance. Paul Davies is an anti-creationist, but he's also the professor of Arizona State University, a professor at Arizona State, and he's the director of the SETI. In 2005, he took the chair of the SETI program, Post-Detection Science and Technological Task Force of the International Academies of Astronomics. What is the SETI program? Search for Extraterrestrial Intelligence. Paul Davies says, it is a shame that there are precious few hard facts when it comes to the origin of life. The how part has everyone stumped. No one knows how a mixture of lifeless chemicals spontaneously organize themselves into the first living cell. He continues, many investigators, he says, feel uneasy about stating in public that the origin of life is a mystery, even though behind closed doors they freely admit they are baffled. Why? They worry that a frank admission of ignorance will undermine funding. Who was Francis Crick? He was one of the co-discoverers of the DNA molecule. He says an honest man, armed with all the knowledge available to us now, could only state that in some sense the origin of life appears at the moment to be almost a miracle. So many are the conditions which would have had to have been satisfied to get it going. In his book, Life Itself, where this quote came from, he proposed his own theory about how life then originated on Earth. And this is the focus of much of NASA's research in what's called exobiology or astrobiology. They know now that the probability of life originating here is so small that they hope to find that it might have originated some other place. And that's why they're looking so intensely for water on Mars and these kind of places, for bacteria on comets. And Francis Crick proposed what's called directed panspermia. He actually believes that some civilization, some ancient some civilization out there in the cosmos somewhere intentionally seeded Earth with life. But that just postpones the formation of any theory. You're still going to have to explain the origin of that life, right? The Bible says, "For the time will come when men will not put up with sound doctrine. Instead, to suit their own desires, they will gather around them a great number of teachers to say what their itching ears want to hear. They will turn their ears away from the truth and turn aside to myths. But for by him all things were created, things in heaven and on earth, invisible and invisible, whether thrones or powers or rulers or authorities, all things were created by him and for him." I think one of the most devastating things about the theory of evolution is ultimately the impact that it has on our perception of what life really is and what human life really is as well. God created us. He created us for a purpose. He created us because he loved us and wanted to have a relationship with us. And the theory of evolution destroys that, destroys what a person thinks of himself. For we are God's workmanship, created in Christ Jesus to do good works, which God prepared in advance for us to do. He loves us. Don't forget that. Life is not an accident. It wasn't by chance. Father, we thank you so much that you did create us, and we thank you even more that you sent your Son, that you loved us so much, that you sent your Son, and Jesus, that you died for us, died to pay for those sins. Father, we love you. Jesus, we thank you. Thank you in Christ's name. Amen. Thank you, guys.